This lesson is the third lesson in the nuclear physics module, and it will be covering fission and fusion. And this is actually the last lesson of this module as well. So the difference between fission versus fusion, and we're going to talk about the different scenarios of both, but here's just a quick overview. To release the energy in a nucleus, we must change that nucleus. So fission is the splitting of a heavy nucleus into lighter nuclei, and fusion is the combining of smaller nuclei to create a heavier one. So these are opposite reactions. In both cases, the mass of the particles change and the energy is released or absorbed. The first time fission was discovered was in 1938 by German scientists who actually shot neutrons at a sample of uranium-235. They were actually trying to add to the sample, but instead it broke apart. So the result was smaller daughter nuclei. So you can look at the equation below that you see that uranium split into other daughter nuclei or different elements. Notice that 3 neutrons are released. Each of these could strike an additional uranium atom and initiate a more decay. So this is a chain reaction, and this is what actually happens in a nuclear bomb. Fission is not a naturally occurring event. It has been found that there is a minimum mass needed to have a chain reaction because the mass is too small, too many neutrons actually escape. This minimum mass is called the critical mass. So if there is enough mass that we can have an uncontrolled chain reaction, the result can be a nuclear bomb. This is the reason only a few countries in the world have nuclear bombs. It must be the perfect ratio. When an atom goes through radioactive decay, a tiny amount of mass is converted to energy. The famous Einstein equation, E equals mc squared. E is the energy, m is the mass, and c is the speed of light. This shows us how converting even a tiny amount of matter can produce a large amount of energy. Some of the uses of fission. The main use for nuclear fission are found in power plants. Countries use different strategies to weaken or deaden the reaction. Some use water, some use graphite. Most reactors use uranium-238 as fuel and have rods that absorb neutrons. By controlling the amount of neutrons that are absorbed, the rate of reaction is and can be controlled. The heat produced by this reaction turns water into steam, which uses to spin a generator, then produces electricity. Fusion occurs when 2 light nuclei collide and combine to make a heavier, more stable nucleus. Issue with fusion is that it requires a very, very high temperature of the atoms to cause that collision. So because of each nucleus is positive, each atom in the collision has to have that very high velocity. This means that these occurs at very high temperatures. These temperatures are so high that they cannot be found on Earth. It would be like being on the sun. Because that temperature gets so high that the material is not a gas state, it's more of a plasma. It is basically creating a sun on the Earth. That temperature is 1.5 times 10 to the 7th Kelvin. The only current way to get such a temperature on the Earth is to explode a hydrogen bomb. In fact, it is fusion that occurs in stars and is responsible for the huge amounts of energy that is released. If humans can ever learn to control fusion, we would be able to produce large amounts of energy by combining hydrogen and making helium. However, we have not figured out a way to control it yet. Now here are the practice problems. The first one states the fusion of hydrogen to produce helium is given this reaction. So there's the equation below. Each deuterium atom, hydrogen-2, has a mass of 2.01410177812 U. Helium-3 has a mass of 3.016029 U. And the mass of a neutron is 1.0086649158 U. What is the energy released when the 2 moles of deuterium fuse to produce helium-3? So this is going to piggyback on some of the earliest lessons in this module. So remember that a mass of a mole is the same as a molar mass, but with a G instead of a U. So the change in mass is the difference between the reactants and the products. So we have to find the change of mass first. So we add what's given to us in the problem, this, and two of them because hydrogen has two, minus this, plus the neutron, and we should get 0.003342 grams. So now we're going to convert it to kilograms by dividing it by 1,000, and we should get 0.00003342 kilograms. So now we're going to use that famous equation E equals mc squared by having that mass in kilograms times 3.00 times 10 to the 8th squared, and we should get, and if you're wondering where this number comes from, remember it's the speed of light, so we should get 3.01 times 10 to the 11th joules. The fusion of two deuterium hydrogen-2 to produce titanium hydrogen-3 and hydrogen produces 6.46 times 10 to the negative 13 joules of energy. How much mass is lost in the process? So again, E equals mc squared. We don't know m, so we rewrite the formula, E divided by c squared. Plug in what we know. We have the energy of 6.46 times 10 to the negative 13. And we're going to divide that by the speed of light. And if we plug that into the calculator, we should get 7.18 times 10 to the negative 30th kilograms. So now we're going to complete the following fission reactions. So we see that the nucleon's 14 plus 1, we see a plus, and this is the mass, so we should get 15. Same thing down here, 7 plus 1 would be 8. We look at the periodic table to find which element symbol follows those categories, and it would be O for oxygen. So that would be the answer here, pretty simple. Same thing down here, since we have this hydrogen, you're going to do 16 plus 16 minus 2, because remember 2 is going to be released over here in this atom. So that would be 30. Same thing down here, 8 plus 8, but remember minus 1 because there's one more over here. So you should get 15. And look at the periodic table for that symbol, and it should be P. So again, just to make sure you're following this, these numbers on one side of the arrow must equal the numbers on the other side of the arrow for both the top and the bottom, so they should be equal to one another. So that arrow, if you want to think of it as an equal sign, to help you solve those problems, you can. And I think that's it for this lesson. Please let me know if you have any questions. Thanks for watching.